When people ask how many satellites Earth orbit can sustain, it sounds like a question that should have one neat answer. A number, a red line, safe below this, dangerous above it. But orbit does not really work like that. There is no single carrying capacity figure for space. Sustainability depends on where the satellites are, what kind of orbits they use, how long they stay there, whether they can maneuver, how good the tracking data is, and what happens to them at the end of their missions. That matters because orbit is not one place. It is a stack of very different environments. Low Earth orbit, or LEO, is crowded because it is useful for Earth observation, communications, science, and crewed missions. Polar and sun-synchronous orbits are especially valuable for imaging and weather satellites because they pass over many parts of the planet in consistent lighting conditions. Medium Earth orbit hosts systems like navigation infrastructure. Geostationary orbit, far higher up, is the famous ring where satellites appear fixed over one point on Earth, making it essential for communications and broadcasting. Then, there are highly elliptical orbits serving more specialized needs. Each of these regions has its own traffic patterns, physics, and risk profile. One of the biggest differences is time. In lower altitudes, the thin upper atmosphere still creates drag. That drag slowly pulls objects downward, and eventually many pieces of debris burn up on re-entry. In that sense, lower LEO has a kind of natural cleaning mechanism. It is imperfect, but it exists. Higher up in LEO, that cleanup effect becomes much weaker. Debris can remain for far longer, which means mistakes are not quickly erased. They linger, and they accumulate. That is why altitude keeps coming up in discussions about orbital sustainability. Around 500 kilometers, debris may persist for comparatively manageable periods. That does not mean safe or simple, just more forgiving than higher bands. Around 800 kilometers, conditions become less comfortable. By roughly 1,000 kilometers, collisions can produce fragments that remain for many years. In those regions, the consequences of a breakup are much more persistent. A single bad event is not just a momentary crisis. It can become a long-running hazard for everyone who uses the same orbital neighborhood. The broad evidence for concern is well established. Estimates regularly published by organizations such as the European Space Agency show tens of thousands of catalogued orbital objects, including well over 10,000 active payloads. And those are only the objects large enough to track and catalog reliably. The actual orbital population is much messier. Dead satellites, uncontrolled objects, old rocket stages, and fragments created by explosions, collisions, and anti-satellite tests. Space is not just full of functioning spacecraft. It also contains the leftovers of previous decades of activity. Beyond that visible inventory lies the more uncertain but serious part of the problem. There are millions to well over 100 million smaller fragments that cannot all be tracked individually. The exact number depends on size thresholds, models, and ongoing observation, so certainty here is limited. But the core point is robust. There are vast numbers of tiny objects in orbit, and many of them are too small to monitor one by one. That matters because orbital velocity makes even a small shard dangerous. A fragment too small to dodge can still puncture, disable, or destroy a satellite. And the reason any of this matters is that satellites are no longer optional extras. They underpin communications, weather forecasting, Earth observation, navigation, precise timing, scientific research, military reconnaissance, early warning systems, and crewed stations. They support financial networks and transport systems. They help ships and aircraft operate. They help emergency responders understand fires, floods, storms, and conflict zones. If important orbital bands become harder to use, the effects do not stay in space. They come down to Earth very quickly. This is where the phrase Kessler syndrome enters the conversation, often in a dramatic way. Properly framed, it is not an instant sky-locking apocalypse where all spaceflight suddenly ends. It is a self-reinforcing process in which collisions create debris, and that debris raises the chance of further collisions, especially in certain orbital regions. If debris is produced faster than natural removal or active countermeasures can clear it, conditions can worsen over time. Some bands could become progressively more hazardous, even if the rest of space remains usable. That said, the strongest evidence against alarmism is also important. Not every collision triggers a cascade. Not every new satellite is automatically a problem. And high object counts, by themselves do not mean humanity has already lost control of orbit. Risk depends on behavior and design, not just totals. A large dead satellite or an abandoned rocket body with no maneuvering ability may pose more danger than several modern satellites that are tracked, responsive, and designed to deorbit after their missions. That distinction often gets lost in simplified debates. Still, the current trend is clearly adding pressure. Mega-constellations, made up of large numbers of satellites, increase conjunction alerts, avoidance maneuvers, and coordination burdens. They place more weight on software, automation, and the reliability of tracking data. They also make the system more dependent on communication between operators, because a close approach is not just a mathematical event. Someone has to decide who moves, when, and based on what information. As the number of active spacecraft grows, so does the need for shared standards and trust in the data. At the same time, there is real countervailing evidence in favor of these constellations. They bring genuine benefits, especially satellite internet for remote regions, ships, aircraft, disaster recovery, and crisis areas where terrestrial infrastructure is weak, damaged, or non-existent. So this is not a simple story of reckless growth versus obvious restraint. It is a trade-off between valuable services and rising operational complexity. And even well-designed systems are not guaranteed to stay well-behaved. Maneuverability is fragile. A satellite can become a hazard through fuel shortages, communication loss, software failure, power problems, space weather, or a small impact. A spacecraft that starts life as a responsible, trackable, maneuverable asset can end up drifting as an uncontrolled object. That is one reason sustainability depends so heavily on end-of-mission behavior and on what happens when things go wrong, not only when everything works as planned. Small fragment risk makes this even harder. Large satellites can often be tracked. Big debris can sometimes be predicted and avoided. Tiny fragments are structurally more difficult to manage. Many cannot be detected well enough for timely warnings, yet they still carry enough energy to do serious damage. That means space traffic management is not just a matter of counting active satellites or coordinating big objects. It also depends on reducing the production of fragments in the first place. Geostationary orbit needs separate treatment because its main problem is somewhat different. GEO is not usually described in terms of the same kind of dense debris swarms associated with parts of LEO. Instead, the issue is the limited number of highly valuable positions, the need for radio and physical coordination, and the importance of moving retired satellites into graveyard orbits so the main belt remains usable. In GEO, sustainability is less about atmospheric cleanup, because there basically is none, and more about preserving a scarce and strategically vital zone through careful long-term management. There are also areas where uncertainty remains important. Many orbital population estimates are regularly published by institutions such as ESA, but not every question is settled. Some claims, especially around cumulative reentry effects and broader environmental impacts, remain subjects of ongoing research or debate. That does not weaken the case for caution. It simply means source criticism matters. Some parts of this topic are measured directly, some are modeled, and some are still being argued over in the scientific and policy communities. So how many satellites can orbit sustain? The most honest answer is that sustainability is not governed by satellite numbers alone. The main danger is more likely dense use combined with long-lived debris, old uncontrolled objects, fragmented governance, and delayed mitigation. In some orbital bands, outcomes may remain manageable if operators can track well, maneuver reliably, coordinate effectively, and remove or deorbit spacecraft responsibly. In others, especially where debris persists for many years, the risks could worsen if traffic grows faster than the systems meant to manage it. Space is not full in any simple sense, but some of its most useful lanes are under growing strain. The future ranges from workable, intensively managed use to increasingly hazardous conditions in critical orbital bands. Which path wins will depend less on a magic number and more on behavior, discipline, and how seriously humanity treats the fact that orbit is shared infrastructure, not an infinite dump. Subscribe, enable notifications, and tell us in the comments what space topic we should cover next.